kind of whizzed through those first questions because they are just conceptual questions, but now we get on to calculations. Those always take longer. Certain temperature, the equilibrium constants for this system, 2NO plus O2 goes to 2NO2, so let's write out the expression for Kc, because that's what we're asked for, and we're given all of the concentrations, but notice all of these concentrations are at equilibrium. So we just plug in NO squared is 0.18 times squared, NO is 0.52 squared, O2 is 0.24, and we get Kc 0.499 per molar, being the units for that particular value of Kc. It's very important that as you do these type questions that you're aware when you're given concentrations or pressures, are they starting values, in which case it's a complicated calculation, or are they equilibrium values? If they're all equilibrium values, piece of cake. Okay, question 9 or 10. At equilibrium, a 3-litre flask. Notice that 3-litre flask contains this many moles, this many moles, this many moles. Calculate Kc. Well, again, here's Kc, NO squared, Cl squared, all at equilibrium divided by NoCl squared. Okay, and let's see what we have. We're told at equilibrium. So at equilibrium, this says Cl2 is 1.2 moles in 3 litres. The NoCl, 1 mole in 3 litres. The NO, 7.5 times 10 to the minus 3 moles in 3 litres. So get those values, and now again, just like previous question, throw them in because they're told that's at equilibrium, and we get a nice value of Kc. So question 11, given Kp, 0.395 atmospheres, what's the total pressure of the equilibrium system if there are 100 millimeters of mercury of both PCl3 and PCl5 at equilibrium? So emphasizing the old at equilibrium part, okay? Now, one of the sneaky things here are the units of pressure that I've given you. We're told Kp with pressure in atmospheres. We're told the equation, so we can get an expression for Kp in terms of the pressures. And in order for this to be 0.395 atmospheres, these pressures have to be in atmospheres. Well, we don't know the pressure of PCl3 and PCl5 in atmospheres because we're told it in millimeters of mercury, but we are given the conversion factor. So pop that in, Kp, 0.395 atmospheres, PCl3 in atmospheres, 100 minus 760, PCl5 in atmospheres, 100 over 760, I think I said minus 760, of course I meant over 760, so the only thing we don't know is PCl. So the PCl2, after cancelling various things out, is 0.395 atmospheres. But all the answers were given in millimeters of mercury, so we have to convert the pressure of Cl2 in atmospheres to millimeters of mercury. Well, that's easy. We multiply it by 760. So the pressure of Cl2 is 300. Each of these two is 100. 300 plus 100 plus 100 is 500 millimeters of mercury. Question 12, an amusing one. Given Kc, the value is 16. After equal moles of H2 and I2 are mixed, there are 0.4 moles of HI at equilibrium. How many moles of H2 are present at equilibrium? Well, there's the equation. There is the expression for Kc. And of course, we know Kc, we know HI. We're asked for H2, but we don't know I2. Well, that's okay, because when we set up our SK chart, which is my preferred way to say ICE chart, when we set up the SK chart, no matter how much H2 and I2 we started with, we use up the same amount. And we make twice that amount of the HI. Okay, now we're told that we start off with equal amounts of H2 and I2, so equal amounts of H2 and I2, so the starting thing's the same. Well, if they change by the same, well then that means the equilibrium values are the same. Okay, we don't know what they are, but they're the same. In other words, the concentration of H2 equals the concentration of I2. So pop that in. Kc is 16. Told HI at equilibrium is 0.4, got to square it, and on the bottom was H2 times I2, but the I2 equals H2, so this just becomes H2 squared. Square it both sides, rearrange a little bit, take the H2 up there, bring the 4 down there, and we get H2 at equilibrium, 0.1 moles. Now, 13, certain temperature, we're told Kp. Initially, no NH3 is present, and N2 and H2 are added in their 1:3 ratios. At equilibrium partial pressure, what's partial pressure of N2? This is actually the same pressure, same question as the last one, but with an added little twist. There's our equation. There's the expression for Kp. We, of course, know Kp. We know the NH3 at equilibrium is 10. We want N2. We don't know H2. But that's okay, because again, same SCA chart, we have no NH3 at equilibrium. At the start, we do have change in 2x, and for the N2 and the H2, the N2 changes by minus x, the H2 changes by 3 times as much to give us minus 3x. Okay, now we were told that they were added in a 1:3, so 1:3. They change by 1:3, so at equilibrium, they have to be 1:3. So the H2 is 3 times the N2 at equilibrium. They started off 1:3, they change 1:3, they'll end up 1:3, which is what we got here. N2 or the H2 is 3 times the N2. Let's call that Y, because that's what we want, the PN2. So throw everything in, and we get a nasty little expression. Multiply this out, it's 27y to the 4th, bring it up here. Take the 1 times 10 to the minus 3 down there. And we get y is 7.8, or about 8 atmospheres. Seems complicated, exactly the same concept as the last question. Just now, instead of 1:1, it's a 1:3 ratio. So moving on to actually the next type of question, but first of all, carbon monoxide reacts with hydrogen gas to form methanol. There you go. First thing to notice is it's not balanced, so we need to balance it. When 0.4 moles of CO, 0.3 moles of H2 are allowed to reach equilibrium, in other words, they're not at equilibrium, that's the starting amounts, 0.06 moles of methanol are formed, and that is at equilibrium. What's the value of Kc? So, set up our little chart, which I hope you're used to by now. There's the equation. We start with 0.4 CO and 0.3 H2, and we have no CH3OH. Change line, we're going to make X of that, which means we use up X of that and use up 2X of that. So at equilibrium, 0.4 minus X, 0.3 minus 2x, and x. Now this is the purpose of a SCA chart, is that it gets all these different unknowns at equilibrium, or amounts at equilibrium, and gets them in terms of one variable, x. So essentially, when we look at our Kc expression and plug it in, we've now gone from Kc is 3 things ratioed together to where Kc is a function of x. And because you always know the Kc expression, and you can pretty much always work out what the equilibrium values are going to be from a SCA chart in terms of x, many questions just boil down to either you know x, in which case you can be asked for Kc, or you know Kc, in which case you can figure out x. Now in this particular case, we're asked for Kc. Well, if I'm asked for Kc, that means I must know x. How do I know x? Well, I look at the question, and I'm told that 0.06 moles of methanol are formed. In other words, concentration of CH3OH at equilibrium is 0.06, but from the SCA chart, the concentration is x. Thus, x equals 0.06. Pop that in, x 0.06, x 0.06, 2x, 2 times 0.06. Punch it into our calculator, and Kc equals 5.45, and the units meters or molar to the minus 2. 2-litre container is charged with, so in other words, we start with 6 moles of CO, 6 moles of H2O, and the following reaction takes place. So it's starting concentrations in a 2-litre container, do notice that, and we're told that at equilibrium the CO2 is 2.4. Again, what's the value of Kc? So write out the expression, set up our little SCA chart. At the start we have 6 moles of CO, but that's 6 over 2 because it's a 2-litre. 6 moles of H2O, but that's 6 over 2 because it's a 2-litre container. None of these. Change line, nice and easy, because it's a 1 to 1 to 1 to 1 reaction, so we use up XCO and H2O, and we make XCO2 and H2. So at equilibrium, these are the values. Here's our Kc expression. We're asked for Kc, which means somehow we know all these values, which means we know X. How do we know X? Well, we're told that at equilibrium, the CO2 is 2.4. So in other words, X equals 2.4. So pop all that in. We get Kc is 2.4 times 2.4, or 3 minus 2.4 times 3 minus 2.4. So simplifying it, lots and lots of squareds. Plug it in our calculator and we get Kc is 16. Same idea as the last question. You're given starting amounts and one equilibrium amount. You use that one equilibrium amount to figure out all the equilibrium amounts. Then you can get Kc. The only sneaky bit here was I told you that we had a 2-litre container and the number of moles. So you had to remember to divide by 2 here. So the following reaction, rigid 3-litre container filled with pure NOBr at a pressure of 4. After equilibrium established, the partial pressure of NOBr 2.5. Okay, so again, telling you starting concentrations and equilibrium, starting pressure and equilibrium pressures was Kp. There's the reaction, there's the Kp expression. Here's our SCA chart. We start with 4 atmospheres of NOBr, so therefore the 3-litre container in this case, who gives a crap other than it's telling us is rigid, and so the concentration or the volume stays the same, but we're interested in pressure, so we don't need to know the volume. So anyway, we start with 4 NOBr, none of these. Looking at the coefficients, 2, 2, 1, so 2, 2, 1, and of course we use up reactants, so at equilibrium 4 minus 2x, 2x and x. Now, we want Kp, so it means somehow we're told X. How are we told X? Well, after equilibrium was established, so in other words, at equilibrium, the pressure of NOBr was 2.5. So, the NOBr is 2.5, but it's also 4 minus 2x. So 4 minus 2x is 2.5. Plug it in, x is 0.75. So now we can replace that everywhere. The NOBr is 2.5, the NO is 2 times x, 1.5, and the Br is just x, 0.75. Pop that in, do our calculation, Kp, 0.27. Now a fun one, which actually occurs in concept 3 times during this particular worksheet. 10 gram sample of solid NH4Cl. Did you notice that slight emphasis? At equilibrium, total pressure. So let's see what we got. Here's our SCA chart. We got NH4Cl that we started with, but we really don't care because it's a solid. We didn't have any NH3 and HCl at the start, which means we make X of each of those. So that equilibrium, we've got X of each of those. And those are the gases that are contributing to the pressure. Kp is, of course, the pressure of NH3 times the pressure of HCl, again, ignoring the solids. So Kp is x squared. Well, how does that help us? Okay, because we want Kp, so somehow we must know x. Well, let's see what other information we're given. At equilibrium, the total pressure, 2.12 bar. Well, the total pressure is the pressure of NH3 plus the pressure of HCl, which is x plus x, or 2x. So in other words, 2x is 2.12 bar, x is 1.06 bar. Pop that in here. Kp, 1.06 squared, or 1.12.